Hey y'all. Today's lesson is, let me move that. Today's lesson is the real number system. I realized I cut off my vocabulary words. The real number system. I'm recording at home because I recorded at school, and then as soon as I finished, I was exporting my video, like trying to save it so I could upload it. And all of a sudden my computer screen went blue and it said, "I'm sorry, we have updates. Frowny face," like colon frowny face. And so whenever it updated and then it restarted, my video was nowhere and I had to leave. So I'm recording at home. You're welcome. Today's lesson is the real number system. We've been talking about decimals, repeating decimals, fractions, scientific notation, integers. We've also talked about roots, square roots, and perfect squares. So those are all fall under the real number system. First, let me give you some vocabulary. A rational number is any number that can be written as a ratio A over B. Can be written as a ratio A over B, where A and B are integers and A and B do not equal 0. Not A times B, but A and B are not 0. Well, I guess A can be 0, but B can't have 0 in the denominator. So any number that can be written as a ratio in the fraction form of A over B. And you're thinking, okay, what exactly do you mean? Well, some examples could be 1/3 is a fraction written with integer numerator and an integer denominator. So 1 is an integer, 3 is an integer, and it's a ratio of 1 to 3. Well, 1 to 3 is also the repeating decimal point through repeating. That means that repeating decimals, because we can write them as fractions, you've already learned to write repeating decimals as fractions. Repeating decimals are rational numbers. Fractions are rational numbers. If it's a terminating decimal, like 1/2 is equal to 0.5, those are rational values because it can be written as a fraction with integers in the numerator and the denominator. Whole numbers are rational numbers like -10 and +50. Whole numbers can be rational, fractions can be rational, repeating decimals, terminating decimals, and then you could have like the square root of 25, which we know is positive or -5, and so the square root of 25 is also rational. The square root of a perfect square will be rational because when you evaluate it, it is an integer. Now, an irrational number cannot be written as A over B. Like it cannot be written as a fraction. There's no equivalent fraction with integers. So where A and B are integers and they don't equal 0. So a few examples of irrational numbers. One number that you've worked with circles, pi is an irrational number because it cannot be written as a fraction. And you might say, well, 22/7, but that is an estimated value of pi. The real value of pi is a decimal that doesn't end. And we round it, we estimate it with 22/7, but it's not real. It's not the real accurate value of pi. Other irrational numbers are square roots. Uh-oh, my dog just came in. Square roots of non-perfect squares. So like the number 30. Cooper, are you going to lay down? The square root of 30 is irrational. Hold on. Hey, Abe or Elle or Ren, can y'all come close this door? Where I'm recording. Cooper just came in. Okay. It's fine that he's in. I just want it closed. Thank you. Okay. The square root of 30 is a non-perfect square. Therefore, close it. Goodbye. So the square root of a non-perfect square. The square root of a non-perfect square is going to be rational because it will never end and it won't repeat. That's why it's an irrational number. So pi, square root of 30. Sometimes you'll see like the square root of 2 a lot is an irrational number. Or if you have a decimal that looks like this, 0.1234 and then ... that is an irrational number because the ... says, okay, this is going to go on and it's a pattern, 1, 2, 3, 4, 5, 6, 7. but it's not stopping and it's not repeating. So that would be an irrational number. So just over here, we have perfect squares are going to be rational. Non-perfect squares are irrational. So that's something for you to remember. So just a little vocabulary about rational and irrational numbers. I need to kind of back this up just a little bit. Okay, how's that? All right, so let's go to the real number system includes both rational and irrational. So when we talk about real numbers, I'm talking about both rational and irrational. Maybe I talked a little bit about what are not real numbers, and technically there is a category called imaginary, and you'll learn about that in Algebra 2. But right now we're just focusing on real numbers, which includes the categories rational and irrational. Rational include these three subsets. We have natural numbers. Natural numbers are your counting numbers. Sometimes they're called counting because when you learn to count, you always start with 1. Nobody says, count and you start at 0. You count with 1. Natural numbers are these numbers in the middle, and those are going to be just your whole numbers counting. Whole numbers, the group right after natural numbers, so you can see, whole numbers are the counting numbers or the natural numbers that includes 0. All right, so it's the counting numbers, the natural numbers, that it includes 0. Natural numbers is a subset of a whole number. Natural numbers are a subset of whole numbers. And natural numbers and whole numbers are a subset of integers. So integers are the set of positive and negative whole numbers. The integers are the set of positive and negative whole numbers. So it takes all the whole numbers and their opposites. So that's why it's positive and negative whole numbers. And whole numbers are a subset of integers. And integers are a subset of rational numbers, which we just talked about up here, rational. So if it's inside, like natural numbers are inside whole numbers, that means it's included in that set. And whole numbers are included in integers, and integers are included in rational numbers. Irrationals are all these other numbers, basically non-repeating, non-terminating decimals, numbers that go on and on but don't repeat. So like pi and non-perfect square roots. All right, so let's do some examples. Example 1, classify each number by determining all the sets, so underline the word all, of numbers to which it belongs. So we have 5 examples. So in A, 0, 1, 6.1616 ... and we can rewrite that, 0.16 repeating, and that means it's a repeating decimal. So because it's a repeating decimal, we know it's a rational number. It is rational because it's repeating, but it does not fit into any of the other categories. It does not fit into natural, whole, or integer. So we're just going to put it out here in rational. So I'm just putting it out there in rational. Letter B, pi. Well, we already said that this is an irrational number. And I'm going to put it over here in the irrational side. 4 1/5. Well, 4 1/5. Can we write it as a ratio of A over B? Do you know how to write a mixed number as an improper fraction? 5 times 4 is 20. 20 plus 1 is 21 over 5. We have successfully written it as a fraction A over B. So that means it's rational. And because it's a fraction, it does not fit into natural numbers, whole numbers, or integers. So I'm just going to put it out here. 4 1/5. All right, letter D, negative square root of 64. So let's simplify that to negative 8. And since it's a whole number, it's an integer, then it is rational. It is a rational number, and it is an integer. So it says we need to list all the sets. So I'm going to put negative 8 in the integer group. It's not a natural number and it's not a whole number, but it is an integer and it is a rational number. All right, the last one, E, the negative root of 10. Well, 10 is a oh man. Can't tell it's Sunday. I just watched like the best Saints game. It went into overtime with the Falcons. Man, it was exciting. We were screaming. My throat kind of hurts because I was screaming. This is a non-perfect square. So if we were to type this into our calculator, we would get some decimal that wouldn't stop and it would not repeat. So this is an irrational number. So I'm going to put it over here, square root of 10, or the negative square root of 10. So when you see these problems, all sets, you're going to list all the sets that the numbers belong to. Okay, the last one, this should say example 2. Use the Venn diagram above to determine whether each statement is true or false. If it's true, explain. If it's false, provide a counterexample. Counterexample is just one example where it proves the statement wrong. It's just you're giving one example where it doesn't apply, the statement doesn't apply, and that's called a counterexample. So A, all rational numbers are integers. All rational numbers are integers. Well, this statement, so if we come up here and look, if a number is in rational, does that mean it's also in integers? And you can see the answer is no. I have 2 numbers out here, so this would be false because I'm just using the repeating decimal. Is rational, but not an integer. So that's a counterexample. All right, B, all irrational are real. So let's come up here and look. All irrational. So any number that falls into the irrational category, is it also a real number? And the answer is yes. Irrational is a subset of real, which means it is true because irrational numbers are a subset of real numbers. And that's what I would expect you to write. The irrational category is a subset of real numbers. And so anything that's irrational will also be real. Letter C, all real numbers are irrational. So we come look, all real. So if we had a real number, does that mean it has to be irrational? And the answer is no, because a real number is going to be rational or irrational. So we just need one counterexample. Can you think of a number that is real but not irrational? And I can. I'm just going to use this one right here. 4 1/5 is real but not irrational. So that's a counterexample. All right, you try D. Press pause. You try D when you get done. Press play. All integers are irrational numbers. All integers. So come over here and I'll look at integers. So integers are right here. All integers are irrational. Well, no, they're not even in the same section. So the answer would be false because -8 is an integer but not irrational. So I hope you got that, and we will practice more in class on the real number system, rational and irrational.